Right now, as you watch this video, a snowball from another star is slipping across our sky, older than our sun, darker than fresh asphalt, bound to nothing we know. Astronomers call it 3I Atlas, the third confirmed interstellar visitor we've ever seen. First came Oumuamua in 2017, then Borisov in 2019. Now number 3 is here, and it isn't following our rules. It was discovered on July 1st, 2025, by Atlas, the all-sky sentry that hunts fast movers against a quiet sea of stars. From the first measurements, one fact stood out: its path doesn't close. This thing isn't from here. It's a traveler from deep time, carrying the chemistry of a different sunrise sealed inside its ice and dust. Telescopes spun toward it and watched a ghost wake, a pale halo, a newborn tail, a faint breath as sunlight warmed the surface and vapor pulled dust into space. You are watching a message in a bottle uncork itself in real time. The glass, the scratches, the scent of trapped gases, these are clues to how other suns build their worlds. Here's the calm part: it isn't a threat. Its closest sweep past the sun is far outside Earth's lane, and its closest pass by Earth is still tens of millions of miles away. It will not fill the sky. It will not shake the ground, but it is rare, and it is precious. We may not see another like it for years. So why the unease from Harvard scientists? Because we've been burned by mystery before. Oumuamua raced by with no clear tail, yet a tiny extra push, and by the time we asked the right questions, the answers were already gone. The fear now isn't doom, it's silence. It's sleeping through a once-only experiment while the universe whispers something we've never heard. This is our antidote to that. No panic, no math lecture, just a clear, human guide to what matters and why. How we know 3I Atlas came from another star, what its light can reveal about alien kitchens, which weird behaviors would actually mean something, and how to tell rumor from signal in the weeks that count. Because there is only one thing worse than an interstellar visitor we don't understand. An interstellar visitor we never really tried to understand at all. Let's open the bottle, read the note, and see what 3I Atlas is really trying to tell us. Before dawn, the sky looks timeless, but buried in that stillness, a faint speck is doing something our homegrown comets almost never do. It isn't looping around the Sunday. It is drawing a one-way arc that opens to infinity, the celestial version of a door that swings out and never swings back. That simple shape is the first clue to what 3I Atlas really island. Here's the plain English story of how scientists learn that. Night after night, telescopes take pictures and note the speck's position against background stars with high precision. If the best fit curve is a closed loop, you're looking at a member of the sun's family. If the curve refuses to close and keeps opening like a flung gate, you've found a hyperbola, an unbound path. Hyperbola is just a fancy way of saying the object has enough energy to escape the sun forever. Could a local comet fake that? A close kick from a giant planet can nudge a long-period comet barely above escape speed. Those imposters look different. Their paths carry the fingerprints of whatever kicked them, and their speeds at the crest of the hill are only a whisper above bound. An interstellar visitor arrives with confidence to spare, and from a direction that doesn't trace back to a recent solar system slingshot. It's the difference between a car that crawls over a hill and one that rockets over it without slowing. That's the geometry. The psychology is another story, and here Harvard voices get loud. In 2017, we watched Oumuamua glide by without a classic tail, and with a tiny non-gravitational push that sparked debate. By the time we realized we were holding a puzzle, the puzzle had left the table. Many researchers vowed not to be late again. The fear, if you want to call it that, isn't doom. It is missing the short window when the object is bright, near, and changing in ways that reveal its nature. So what does the new playbook look like? Step 1 is motion, measured obsessively. As the sun warms a comet, jets of gas whisper off its surface. Those jets act like invisible thrusters and gently bias the orbit. If we track the position to hair-fine accuracy, any steady drift from pure gravity will show up. That drift tells us how active the nucleus is and can even hint at how it is spinning. Step 2 is brightness, measured through colored filters and polarizers. Dust grains scatter sunlight in ways that depend on size and texture, and the scattered light can be polarized, lined up like tiny vibrating strings. Those clues let astronomers tell smoke-fine dust from sand-coarse dust, and smooth grains from fluffy clusters. Meanwhile, gas emits its own faint glow. If carbon monoxide, carbon dioxide, or simple water vapor dominates, the comet's color balance shifts in recognizable ways. Step 3 is spectra, the prism trick. Split the light into thin stripes and molecules announce themselves by name. If 3I Atlas grew up around a cooler red star or in a colder nursery, its ice mix could be unusual. We have a hint from the last interstellar comet, Borisov, which looked normal to the eye yet carried signs of a chilly origin. If 3I Atlas shares that recipe or defies it, we learn how diverse other planetary kitchens really are. Step 4 is coordination. This is a team sport. Big observatories chase fine details. Space telescopes dodge the blur of our atmosphere. Skilled amateurs fill gaps the pros can't cover. The goal is continuity. No multi-day holes where the activity might spike, the spin might change, or the path might kink. A once-ever flyby deserves a full-court press. Let's clean up 2 common confusions. First, interstellar does not mean dangerous. A hyperbola guarantees it is leaving. Closest approach to the Sun and to Earth may make headlines, but close in astronomy usually means very far in human terms. Second, odd does not mean artificial. Nature builds strange. If we see a gentle push from outgassing, that is a comet doing comet things. If we don't, that tells us something too. Perhaps the surface is crusted over, or made of ices that vent quietly. There are pitfalls. Size estimates are slippery early on because brightness is a blend of the nucleus plus whatever dust it sheds. A dark, compact object can masquerade as larger if it's dusty. A bright, reflective one can look larger even when it's bare. Activity can also flicker. Sunlight turns ices to vapor, but veins of more volatile ices can erupt in pulses. That is why careful teams resist dramatic claims on day 1 and keep updating as new data land. If you're following along at home, here's your viewer's guide. Watch whether the tail grows smoothly as 3I Atlas nears the Sun or surges in bursts. Watch for small, steady deviations in its predicted path. Those are the fingerprints of jets. Listen for talk of color and polarization. Those words translate to grain size and chemistry. And listen for spectra, the barcodes of gas. If the reports say water-rich, you're hearing a warmish recipe. If they say carbon monoxide-rich, you're hearing a colder kind of birthplace. Wrap all this together, and you see the heart of the concern at Harvard and beyond. The stakes aren't about drama, they're about clarity. A traveler from another star has wandered into our lab, and the experiment runs exactly once. The only way to fail is to look away, to let the numbers go unmeasured, to let the questions go unasked. So we measure the motion, we read the light, we split the spectrum, we keep watch. Because when a messenger crosses an ocean of darkness to knock on your door, the respectful thing is to open it, take notes, and learn. We learned our caution the hard way. In 2017, a thin sliver from another star slid through the inner solar system and refused to behave. It brightened and faded oddly, showed no obvious tail, and yet drifted a hair off the path gravity alone would draw. By the time we aimed our finest instruments, it was already leaving. That visitor, Oumuamua, left us with blurry pictures, heated arguments, and one clear lesson. If you want answers, you need dense data early. What made Oumuamua so slippery was not mystery for mystery's sake, but how many natural explanations could fit the limited evidence. One idea said it vented gas like any comet, quietly, with jets too smooth or dust-free for us to see. Imagine a hairdryer taped to one side of a snowball. Another said sunlight pushed on an object that was extremely light for its size, the way wind fills a sail. Others proposed exotic ices that evaporate invisibly, or a porous dust bunny so airy that light pressure could matter enough to nudge the path. With so little data and no second chance to look, the debate never truly closed. That memory shadows everything about 3I Atlas. On the surface, this one looks more straightforward. It is clearly switching on like a comet, sprouting a coma and tail as sunlight wakes up frozen gases. That already puts it in a different class than Oumuamua's bare, puzzling pass. But vigilance is still wise, and this is where Harvard's louder voices come in. The fear is not monsters. The fear is missing the tiny tell, an almost invisible drift, a faint color change, a rhythmic flicker that would have separated the normal from the strange. So what would make eyebrows rise now? First, a steady, directionally consistent push that does not line up with ordinary jets. Comet jets are messy. They turn on and off as the nucleus spins and as vents face the sunday. A smooth one-way nudge that ignores the spin pattern would be unusual. Second, a brightness rhythm that ticks like a clock, bright, dim, without matching signals of gas or dust. Third, abrupt changes in path or spin after a hard solar heating that do not match the volatile ices we expect to wake up. None of these would scream artificial, but all would demand tougher tests. The tests for these ideas are concrete. Track the position night after night and compare it to gravity's clean prediction. Early or late arrivals at each checkpoint map the invisible forces. Split the light with a prism and look for the barcodes of gas. If the extra push grows when carbon monoxide lines strengthen, jets likely drive it. If there is a push with no gas lines and little dust, look harder. Measure polarization, the way reflected sunlight lines up after bouncing off tiny grains, to infer dust size and texture. Watch the rotational light curve. If the brightness pulses match a spinning, irregular body, jet-driven changes should come and go as different active patches turn toward and away from the sun as expected. Here is where the real worry lives. It is not about danger to Earth. It is about the temptation to shrug and move on. Harvard's call is simple. Do not let 3I Atlas slide into the bin marked probably typical without earning the label. The cost of overmeasuring is telescope time. The cost of undermeasuring is another decade of speculation. Since 2017, the community has upgraded its playbook. Survey telescopes trigger target of opportunity time on big observatories before the window closes. Teams pre-write checklists so the first clear nights are not spent debating what to do. Data are shared faster. Skilled amateurs extend coverage with backyard photometry, filling gaps the pros cannot. When the orchestra plays in time, single instruments do not have to shout. Why work this hard? Because each interstellar visitor is a sample from a foreign construction site. Dust grains record the temperatures and pressures of the nursery that built them. Ices tell us which ingredients were abundant and which were rare, and how far from their star those ingredients froze. The mix of gases maps chemistry. The level of activity maps structure. The spin changes map where the jets live. If several visitors tell the same story, we learn that planetary systems share a recipe. If they disagree with each other, we learn that world building is a messy art. Either way, the payoff is big. We move from one-off anecdotes to patterns. Also, keep in mind that the strangest outcome would still likely be natural. Space manufactures oddities by the billions. A wafer-thin shard can peel off a larger body and tumble like a leaf. A porous aggregate can feel sunlight like a sail. A crust of unusual ice can seal the surface, so gas slips out quietly through cracks. None of that requires intention. All of it requires careful measurement to tell apart. For you and me, a few phrases will act like signposts. Consistent with outgassing means the extra push, if any, lines up with normal comet behavior. Radiation pressure means sunlight is doing measurable work, which points to very low mass per area. Non-gravitational acceleration with no gas detected is the one that lights debate. It does not prove anything dramatic, but it guarantees long nights comparing models. If we secure the clean measurements that 2017 denied us, we will not just answer a headline, we will build a template for the next traveler. We will know which instruments to point, which alarms to set, which patterns are benign, and which deserve a second look. That, more than any science fiction speculation, is why some Harvard scientists push so hard. Their fear is that the universe is offering a new clue, and we are too casual to notice. Their hope is that this time we will treat the clue like gold. Curiosity is the safest stance. Point the telescopes, share the data, ask the uncomfortable questions. Let evidence, not wishful thinking, decide what 3i Atlas really island. Let's zoom out and ask a simple question. How do you even make something like 3i Atlas? Start with a young star wrapped in a disk of gas and dust. Planets form like pebbles rolling into boulders, and the big ones, giant planets, act like cosmic goalkeepers. With every close pass, they punt leftover ice balls outward. Most get parked in far cold storage. Some are launched so hard they clear the stadium and never come back. Our sun likely did this. Other stars did it too. Over billions of years, the Milky Way filled with drifters, a slow snowfall of ancient objects between the stars. That is why the chemistry matters. The recipe frozen into a comet encodes the temperatures and pressures where it was born. Water ice forms easily. Carbon monoxide and carbon dioxide prefer colder shelves. Grains of dust carry coats of organics, smoky, tar-like films baked by radiation. When sunlight wakes a visitor, that pantry vents into space. Split the light, and you read a barcode. It is like smelling a kitchen when someone opens the oven. Harvard's worry lives right here, in the difference between a shrug and a finding. If we treat 3i Atlas as just another fuzzy streak, we risk a false negative, missing an important clue because we assumed the ordinary. If we let wild speculation lead, we risk a false positive, announcing a headline that collapses under better data. The guardrail is simple. Define the tests in advance, collect clean measurements, and let the numbers choose the story. What would a telling pattern look like? One sign would be a gas mix that skews colder than most local comets. Strong carbon monoxide lines early, for example, hinting that this object grew up far from its star or around a dimmer Sunday. Another would be an unusual dust texture. Smooth, compact grains scatter light differently than fluffy clumps. Polarization reveals that difference. A third would be timing. If the comet turns on earlier or later than thermal models predict, the surface may be crusted over, riddled with vents, or loaded with uncommon ices. Motion tells another part of the story. Jets act like tiny thrusters. As different vents rotate into sunlight, the push changes. That wobble writes a light curve, bright, dim, bright, as the nucleus spins, and it slightly tugs the orbit. With enough nights of data, astronomers can invert that flicker into a rough map of shape and spin, a bit like reconstructing a sculpture from its shadow. If the push grows when certain gases flare, the case for ordinary outgassing strengthens. If a steady nudge appears with little gas or dust, the team will look twice. None of this demands heavyweight math to follow. Think of a playground merry-go-round. If a child runs up and gives it a shove every time a red stripe passes, the ride speeds up rhythmically. Swap the child for a sunlit jet, the red stripe for a rotating vent, and you have comet talks. We are simply watching for whether the shoves match the stripes. Along the way, we should retire a few myths that muddy public discussion. A long tail does not mean fast forward. Tails point away from the sun like windsocks, no matter which way the comet is traveling. Brightness does not equal bigness. A small, dusty object can outshine a larger, clean one, and Interstellar does not translate to rare danger. The defining feature of a hyperbolic path is not doom, it is departure. So why link this to Harvard at all? Because institutions and voices matter when setting the tone. The loudest message from Cambridge is not panic, it is preparation. Have the checklists ready. Trigger observations early. Compare models in public. treat the window as precious. That mindset is less about fear of aliens and more about respect for evidence. We do not get to schedule interstellar visitors. They arrive with their own clocks. There is also a human reason to care. Moments like this reset our sense of scale. We live on a warm rock circling a star, and yet across the gulf between stars, debris still finds us. A mote of ice can travel for ages, cross our orbit for a few brief months, and leave forever. If we learn to read even one of these motes well, we shorten the distance between out there and right here. That is worth patience, and it is worth care. You do not need to memorize molecule names to follow the plot from your couch. When you hear observers talk about spectra, think ingredient list. When you hear polarization, think texture. When you hear non-gravitational acceleration, think gentle push from jets. When you hear light curve, think spin rhythm. Those 4 ideas will carry you through almost every update without drowning in jargon. And if, after all the watching, 3i Atlas turns out to be delightfully typical, that is still a win. Typical is data, typical is a baseline. The next visitor can be compared against it, and the next after that. Patterns emerge. Maybe interstellar comets are often colder. Maybe their dust is fluffier. Maybe their surfaces are more crusted from long years in deep space. Either way, we trade guesswork for knowledge. Picture a lab that opens for a few weeks every few decades. The experiment runs once. The sample can't be brought back. If you miss a measurement, there's no makeup day. That's the emotional core behind Harvard's caution about 3i Atlas. Not fear of monsters, but fear of losing a clean answer to noise, delays, or wishful thinking. So the plan is to set traps, evidence traps, before surprises arrive. The first is the geometry trap. Astronomers compute where the comet should be, if only gravity acts, then watch for departures from that clean line. If the offset grows and shrinks with a steady rhythm that matches the object's spin, jets are doing the pushing. If the offset has a one-way bias that ignores the spin rhythm, that's interesting and demands extra checks. The second is the light trap. Split the light and look for the signatures of ordinary gases. Water, carbon monoxide, carbon dioxide, and faint carbon chains all leave fingerprints. If a gentle push appears when those lines strengthen, that's a comet behaving like a comet. If a push appears with no gas and very little dust, the team doesn't shout artificial. They ask whether instruments missed something, whether the gas vents quietly, or whether sunlight pressure on an unusually light object could be enough to explain it. The third is the texture trap. Polarization, light waves lining up after bouncing off dust, changes with grain size and fluffiness. Think polished pebbles versus clumped ash. By tracking how polarization evolves as 3i Atlas warms, observers can tell whether the dust is mostly smooth and compact, or feathery and porous. Texture feeds back into dynamics, because fluffy dust drifts more easily and can masquerade as a brighter, larger object than it really island. The fourth is the timing trap. Teams pre-announce what they'll measure and when. That keeps everyone honest and prevents cherry-picking the weirdest night. If the tail length or gas ratio changes suddenly after a burst of sunlight, that timestamp matters. If a claimed anomaly shows up in one team's data and not in another's taken minutes apart, the burden of proof shifts. There's also the glint trap. Flat, mirror-like facets can flash when the sun, the object, and a telescope line up just so. Natural fragments can glint too, but a repeating, razor-sharp flash with a constant period would be notable. To test it, observers at different locations compare notes. If two telescopes half a world apart see the same heartbeat at the same moment, pay attention. If only one sees it, suspect clouds, calibration, or a satellite streak. And then there's the radio trap. No one expects a narrowband beacon, but while the optical giants work the light, radio telescopes can listen in the background. The rule is simple. Extraordinary claims require extraordinary redundancy. If the optical data hint at something odd, independent radio silence, or radio confirmation helps keep the story grounded. Harvard's role in all this is cultural as much as technical. The message from that campus and its collaborators is to treat interstellar visitors like time-critical fieldwork. Draft the checklist now, share raw data quickly, invite rivals to replicate you, pre-register the questions you'll ask. That mindset resists two failure modes: seeing faces in clouds and refusing to see a face even when it smiles back. False positives are everywhere. Cosmic rays can fake a sparkle. Satellite trails can slash an exposure. Twilight can bias colors. A warm mirror can mimic a faint glow. Even honest math can mislead. Fit too many parameters to a small dataset, and the curve will happily tell you any story you want to hear. This is why the community talks so much about cadence. Lots of short, repeated observations, not a single pretty photo. Cadence turns rumor into measurement. Zoom out, and you see the stakes beyond this single object. For now, interstellar detections are rare, so every data point carries outsized weight. Soon, that will change. Next-generation surveys will flood the sky with moving object alerts. When that era begins, today's careful methods will scale from one case to dozens. The Harvard fear will soften into routine, not panic, just process. But we're not there yet, and that's why people speak with urgency. If 3i Atlas turns out textbook normal, we still win. We bank a reference, calibrate our tools, and learn how an interstellar comet behaves when nothing weird is happening. If it turns out to be quirky, we also win, because the traps are set to catch the quirk with numbers, not adjectives. What about meeting a future visitor up close? Space agencies are already exploring that play. A waiting probe parked near Earth could sprint toward a newly discovered object and sample material in flight. Another idea is a modular chaser that can launch on short notice and assemble in space. None of this is science fiction. Pieces are on drawing boards now. The key is readiness. If discovery windows last weeks, intercept plans must live on shelves, not in imaginations. Here's a viewer's guide for the months ahead. If observers report a steady, spin-matched push alongside gas lines, they're seeing jets. If they report a push with no gas and no dust, they won't jump to conclusions. They'll ask sharper questions and invite more instruments. If a repeated glint appears from many sites, they'll test it to death. And if everything aligns with ordinary physics, they'll say so plainly. Boring is beautiful when you're building a baseline. The bottom line isn't that 3i Atlas is scary. The bottom line is that apathy, island. Harvard's worry is a work ethic. Be ready, be careful, be humble, and let nature surprise you on its own terms. That's how you turn a once-in-a-generation visitor into knowledge we can keep after it vanishes back into the dark. Frame 3i Atlas as a story in 3 acts: inbound, swing by, outbound. Each act opens a brief window for specific answers. That is the whole reason the Harvard crowd sounds urgent. The lab is open now, not later. Miss the window, and a crucial line of the story is gone. Inbound is about origins. Far from the sun, only the most volatile ices respond. If carbon monoxide wakes first, the birthplace was likely colder or farther from its star. If almost nothing wakes, a tough crust may be bottling the gas until the heat rises. Catching that first breath matters most because it is the least contaminated by later changes. The swing by, the weeks near closest approach to the sun, is about behavior under stress. Vents open, jets strengthen, and the spin can change as the nucleus reacts to its own exhaust. Picture a lawn sprinkler suddenly turned to full pressure. The pattern of spray can shove the head into a new wobble. With precise timing, night after night, teams can test whether the push follows the spin, as ordinary jets do, or whether it drifts in a smoother, one-direction way that ignores the rhythm. Outbound is about endurance. After the hot flash fades, what lingers? Do the same vents keep working? Does the dust texture evolve from fluffy to compact? Does the coma shrink along a simple cooling curve, or does it pulse as buried pockets vent one last time? The fade-out is a stress test for every idea we built on the way in. To navigate all three acts, observers track three dials: speed, size, and spin. On a hyperbolic path, the traveler carries excess speed, meaning even after falling toward the sun, it still has energy left to leave forever. That is the giveaway that it did not grow up here. Size is trickier because brightness is a liar. A small, dusty object can look big. A large, dark one can look modest. So teams model dust carefully to separate grain glow from the light of the solid nucleus and pin down the true scale. Spin is the metronome. As the nucleus rotates, active patches take turns facing the sun, and the jets they drive should rise and fall with that rhythm. Red flags and red herrings live side by side, so the plan is to separate them calmly. A red flag would be a steady, non-gravitational push that refuses to line up with the spin and persists even when gas lines are weak. Another would be a crisp brightness rhythm with a strangely quiet spectrum. A third would be abrupt path tweaks that arrive at times when no thermal model expects fresh vents. Red herrings include satellite streaks, twilight color bias, and single-night blips that vanish under repeat exposures and careful calibration. What will teams actually publish? Expect time-stamped sky positions so anyone can fit the path. Expect multi-filter brightness measurements that track color changes. Expect polarization curves that translate to dust texture. Expect spectra that flag the big ice families and show which ones dominate at which distances from the Sunday. When different groups agree independently, confidence soars. When they diverge, that gap often points to the truth, because it forces deeper checks of assumptions and calibration. Now imagine two futures. In the first, 3I Atlas behaves like a textbook interstellar comet. Gas lines rise with solar heating. Polarization points to grains not far from what we see in long-period comets. The small extra push matches rotating jets. The narrative becomes a baseline. This is what normal looks like for a traveler between stars. In the second future, attention remains. Maybe the push is too smooth. Maybe gas is scarce. Maybe the color stays oddly stable when activity surges. None of those would prove anything exotic, but each would keep the tests running. Either way, the next decade will change the game. New all-sky surveys will find more interstellar passers-by, perhaps several in a single season. When that flood arrives, the culture shaped by today's caution, pre-registered plans, rapid data sharing, fast cross-checks, will let us sort patterns from outliers quickly. The Harvard fear will mature into muscle memory. Do the boring things well so the surprising things stand out. There is a public piece to this too. Headlines chase novelty. Some oversell, others scoff. A better habit is to ask 4 questions of any claim. Is the effect repeatable? Does it appear in more than one kind of measurement? Does it track a clear physical cause, like gas lines strengthening as a push grows? And does a rival team see it with a different telescope? If the answers cluster toward yes, you are probably looking at a real signal. If they spread out or lean no, you are probably looking at normal noise or an instrument quirk. At the heart of this is respect. Respect for nature's capacity to surprise us, and for the audience's capacity to handle uncertainty. It is fine not to know on day one. It is better to say we need 3 more nights than to spray confident guesses. The universe is patient. Our job is to meet its patience with craft. So if you step outside on a clear night and think about a dark, ancient traveler sharing our sky for a brief moment, remember the 3 acts and the 3 dials. Inbound is origin. Swing by is stress. Outbound is memory. Speed tells you it is a visitor. Size tells you how much of the glow is dust versus rock. Spin tells you how the jets should push. With those ideas, every update you hear will make sense without equations. Harvard's caution is not a warning label. It is a production plan. Write the questions before the curtain rises. Cue the instruments on time. Capture the lines the first time they are spoken. And when the curtain falls and the traveler fades back into the dark, Make sure the notes are good enough that the story can be told long after the stage is empty. Let's build the perfect stakeout. If you had the world's observatories on speed dial and a single interstellar visitor to study, how would you choreograph the watch? The answer is a relay. Each instrument plays to its strength, hands the baton to the next, and together they turn a short flyby into a complete portrait. Start with wide-field survey telescopes, the night's traffic cameras. They catch motion, set the baseline orbit, and raise alarms whenever the brightness or path twitches. Think of them as the metronome that keeps everyone else in time. When the alert goes out, the medium and large telescopes pivot. Their job is to squeeze detail from every photon. What gases are rising? How fast is the spin? Does the push from jets rise and fall with the rotation the way it should? Space telescopes add clean vision with no atmosphere in the way. Their spectra are crisp, and their sensitivity to faint light is superb. In practice, this means two things. First, they can sniff the faintest gas barcodes, traces of carbon monoxide, carbon dioxide, water, and simple organics that ground-based telescopes sometimes lose in the air's glow. Second, they can watch the small, slow changes that signal torque on the nucleus, because their images are steady night after night. Radio dishes play a different game. They do not care how bright the object looks to your eye. They care about molecules that spin and vibrate at radio-friendly frequencies. When those molecules flip between energy states, they whisper in radio, and a big dish can hear it. Radio data anchor the chemistry and cross-check claims of activity even when dust is scarce. Polarimeters, special add-ons for many telescopes, measure how aligned the light waves are after bouncing off dust. If you picture sunlight as tiny jump ropes, polarization tells you whether those ropes are swinging in random directions or mostly in step. The more in step, the more clues we get about grain size and fluffiness. That, in turn, tells us how easily sunlight might push on those grains and how much of the glow is dust versus the bare nucleus. Even humble backyard gear has a lane. A small telescope with a camera can take many short exposures across a single night, building a light curve that reveals the spin rhythm. When dozens of amateurs do this from different longitudes, they create a 24-hour heartbeat that professional schedules sometimes miss. It is the astronomy version of crowd-sourced weather radar. Now, imagine the timeline. On the way in, the plan is sniff early. If carbon monoxide pops first, you are looking at a recipe born in deeper cold. If the object stays quiet longer than expected, a crust may be bottling the gas until more sunlight leaks in. During the swing by near the sun, cadence is king. Observers want nightly position fixes, spectra, polarization, and light curves, so they can map how jets turn on and how the spin responds. On the way out, patience pays. As the furnace cools, activity should fade along a predictable curve. Any late sputters expose buried pockets and sealed cracks, a kind of aftershock that reveals how the interior is built. Here is where fear of the wrong kind of surprise enters. A single glint could be a rotating flat facet, or just a satellite stray. A sudden color change could be new gas, or the object dropping into twilight, which reddens everything. A tiny path shift could be a jet, or a math fit that tried too many knobs on too little data. The antidote is redundancy. You ask for the same answer in multiple ways: optical spectra, radio lines, polarization, and timing, and from more than one team. If 3 independent paths agree, confidence rises. If they disagree, teams check calibrations, repeat the sequence, and let the claims sit until the instruments converge. Suppose the data do show a gentle, persistent push with little gas and dust, a combination that keeps eyebrows high. Before anyone leaps to headlines, the checklist demands more mundane trials. Could the nucleus be a very low-density, highly reflective slab that sunlight nudges more than usual? Could sublimation be happening but screened by a tight blanket of grains that hides the lines? Could our color filters be biased by air glow or moonlight? Each ordinary explanation must be tested and, if necessary, ruled out with targeted observations before anyone reaches for extraordinary ideas. There is a practical limit, of course. Interstellar visitors sprint through our stage. You cannot point every instrument every night, so teams triage. They rank questions by value per hour. A precise light curve might settle the spin and lock the jet model. A deep spectrum during a predicted outburst might pin the chemistry. A multi-site search for repeated glints might kill a rumor faster than any single fancy image. The plan is not to do everything. It is to do the right things at the right moments. If you're listening rather than watching, you can still follow the play. When you hear target of opportunity observations, think, the relay baton just moved to a bigger telescope. When you hear non-gravitational parameters updated, think, the gentle push number just got an upgrade. When you hear high polarization at phase angle X, translate that to, the dust looks fluffy and bright from this sun object Earth geometry. And when you hear no detection from radio dishes, do not assume nothing happened. Sometimes the molecules sit below detection limits, or their lines fall outside the receiver's bands. Finally, consider the legacy. Every procedure we refine now becomes muscle memory for the next encounter. The fear that Harvard scientists voice is not fear of aliens or disaster. It is the quieter, more useful fear of waste, of letting a rare, clean experiment go muddy for lack of preparation. Treat the window like live theater, rehearse, hit your marks, and make the one performance count. Do that, and whether 3i Atlas turns out textbook normal or stubbornly odd, we will keep the one prize interstellar visitors always offer, clarity we can hand to the future. Call it a checklist for the extraordinary. If 3i Atlas is an ordinary interstellar comet, most of its behavior will fall into familiar grooves. But if any one of 4 signals appears and survives careful cross-checks, the conversation shifts from probably ordinary to pay very close attention. Signal 1 is a push without a breath. Comets travel mostly under gravity, with tiny extra nudges from jets of gas that switch on as sunlight warms the surface. Those jets are the comet's breath. If observers measure a steady, gentle shove that keeps nearly the same direction for weeks while gas lines stay weak and dust remains scarce, that mismatch deserves scrutiny. It could still be natural, sunlight pushing on an object that is unusually light for its size, but the bar for proof rises. Signal 2 is clockwork without a cause. Many small bodies brighten and dim as they spin because irregular shapes reflect more light from some angles than others. That is normal. What would be notable is a crisp, repeating glint that looks like a mirror flash and keeps a fixed beat across many nights and many observatories. Natural facets can glint, but the more precise and repeatable the flash becomes, the more it begs for a multi-site test. Signal 3 is chemistry that refuses to budge. As a visitor nears the sun, different ices should wake at different distances, and the color and spectrum should evolve. If 3i Atlas brightens dramatically but its spectra stay flat and quiet when models expect change, we would ask whether a crust is sealing the surface, whether gas is escaping invisibly, or whether the measurements missed faint lines. A stubbornly quiet spectrum alongside steady non-gravitational push is the combo that keeps eyebrows raised. Signal 4 is a path that drifts the wrong way. When jets push, the tiny course changes tend to line up with the object's spin pattern and with the daily cycle of solar heating. If, after correcting for all that, the orbit still shows a smooth, one-way bias that ignores the rhythm, that is a yellow flag. It does not prove anything exotic. It proves we do not yet understand the source of the push, and that more eyes and more wavelengths should join the watch. None of these signals stands alone. Nature is a master of trickery. A thin sheet of dust can hide gas lines, twilight can repaint colors, a warm mirror can mimic a faint glow. A model with too many knobs can bend any curve to its will. That is why the responsible move is to build a web of cross-checks. If several independent methods point the same way, positions, spectra, polarization, confidence climbs. If they do not, you slow down and look for leaks before reaching for big claims. Stepping back, Harvard's fear is best understood as a discipline. It says, write down the thresholds now, decide which patterns deserve extra nights and which are likely to melt under repetition. Pre-register the plan so that when something odd appears, the response is automatic rather than improvised. That culture guards against two equal and opposite mistakes, chasing mirages and ignoring a real signal because it feels inconvenient. This mindset also helps you pass headlines. When you hear that 3I Atlas shows non-gravitational acceleration, translate that as there is a measurable gentle push, then ask whether gas lines strengthened at the same time. When you hear about a periodic flash, ask whether more than one observatory saw it. When you hear that the spectrum is quiet, ask how far from the sun those spectra were taken. Context turns a rumor into a result you can weigh. There is another layer here, and it is personal. Interstellar visitors make us feel small and lucky at the same time. Small, because they remind us the galaxy is busy without us. Lucky, because one of those wanderers is sharing our sky, briefly. That emotional weight can warp judgment. The discipline is to want the truth more than a thrilling or boring answer. So picture how the next few months unfold if we do this right. The inbound data sketch an origin story. Near the sun, dense cadence locks the spin and pins the chemistry. On the way out, we test how the glow fades and whether the same vents keep breathing. Teams share raw numbers quickly, rivals replicate, and outliers are chased but not married. If 3I Atlas ends up textbook, we get a clean template for the next visitor. If it ends up quirky, we get numbers sturdy enough to carry the debate without hype. And if, against the odds, one of those 4 signals survives every ordinary explanation, we will not need to shout. The data will speak in chorus. Motion, light, texture, and timing will rhyme. At that point, the conversation changes, not to wild claims but to sharper questions. What shape and density would sunlight need to nudge it that much? What kind of crust could hide gas for so long? What viewing geometry would turn a natural facet into a flash so regular? Each answer would point to targeted observations, not speculation. Interstellar objects are not omens, they are opportunities. Harvard's urgency is simply a way to honor the opportunity with craft. Name the thresholds, set the traps, cross-check the clues. And when the traveler fades into the dark again, let the evidence decide what story we get to keep. Names shape expectation. Call 3I Atlas a comet, and our minds summon a familiar picture, icy, venting, harmlessly passing through. Call it an interstellar object and the tone turns rarer, more alert. Add what if, and some people hear sirens while others roll their eyes. Harvard's stance aims down the middle. Keep the calm of comet, keep the precision of interstellar, and keep the door open to what if, without letting speculation run the show. That balance starts with humility about what telescopes can and cannot do. A spectrum tells you ingredients, not a photograph of the kitchen. A light curve tells you spin, not a sculptor's sketch of the shape. Orbit fits are powerful, but a handful of early points can mislead until more nights smooth the curve. When researchers say consistent with, they are not hedging. They are telling you the data allows several futures, and the simplest one is leading. For now, process is the part we control, which is why Harvard voices harp on it. You cannot slow an interstellar visitor. You can decide how you measure it. So they push for living documents, public logs where teams note what they tried, what succeeded, and what failed. It sounds dull until you need to know whether last night's glow was a real change in the object or just a tweak to the instrument. A single line in a log can save a week of rumor. There is also a design principle at work. Measure orthogonally. If one method hints at a push, use a completely different method to check it. Positions on the sky are one angle, spectra are another. Polarization is a third, radio lines are a fourth, light curve timing is a fifth. Like the legs of a table, each is stronger when the others stand with it. If 2 legs wobble, you do not climb on the table and declare a miracle. You fix the wobble or you wait. Here is orthogonality in action. Imagine the orbit fit says there is a gentle extra shove. That is leg 1. The spectra on the same nights show carbon monoxide lines brightening. Leg 2. The light curve's rhythm shifts in step with the timing you would expect if a particular vent rotated into sunlight. Leg 3. Polarization climbs, signaling fresh, tiny grains, debris that jets often loft. Leg 4. When those four align, the natural explanation, ordinary jetting, wins without drama. But say the spectra stay quiet while the push grows. Now, two legs disagree. Before anyone reaches for exotic ideas, the process asks boring questions. Were the spectra taken at a phase angle that makes lines harder to see? Did moonlight or twilight wash them out? Were the receivers tuned to the right frequencies? Could a dust blanket choke the gases while sunlight still nudges an unusually light surface? Each mundane question is a valve that bleeds hype out of the system. A short glossary helps. Non-gravitational acceleration means a small nudge in addition to gravity. Light curve is brightness over time. Spectrum is the rainbow sliced into bars where molecules leave their marks. Polarization measures how aligned light waves are after bouncing off dust. Phase angle is the sun-object-Earth geometry that changes how we see things. With those 5, you can read almost any update and find its heartbeat. Now, about that fear word in our title. Fear is a crude term for a refined instinct. Protect the chance to learn. In medicine, it is sterile tools and checklists. In aviation, it is pre-flight routines and cross-checks. In this business, it is pre-registered plans, cadence charts, and open data. The emotion is not dread. It is respect for one-time opportunities. Harvard's contribution is to make that respect visible and contagious. There is a deeper payoff too. Interstellar visitors push us to separate what we know from what we assume. We assume comets are dirty snowballs, but that phrase hides wild variety. Some are crusted, some fragile. Some carry unusual gas mixes, some barely vent at all. We assume radiation pressure is trivial until a wafer-thin shard proves otherwise. We assume spin is steady until jets twist the nucleus a little every day. Each assumption that bends under new data makes us better readers of the sky. And then there is wonder. Even if 3I Atlas turns out to be ordinary at this scale is astonishing. A relic from another sun, bottled for eons, warming for a few months in our daylight, then gone. If you strip away hype and dread, that is still a near-perfect story of time and chance. The job of good science writing and good science is not to inflate that story. It is to tell it straight, so its natural power can do the work. As you follow the next updates, try a calm ritual. When you see a claim, imagine the table. Ask which legs carry weight. Look for the logbook lines. Translate the jargon with the little glossary. Hold your breath through the first surprising night, and wait for the second. You are not just a spectator, you are part of a culture that rewards patience over thrill, pattern over anecdote, evidence over convenience. 3I Atlas will leave, the notes we keep will not. If we do this well, the next time a stranger from the dark writes a line across our sky, we will meet it with better questions, faster reflexes, and clearer eyes. That is the quiet promise inside Harvard's urgency. Not a warning about what the visitor might be, but a promise about who we can be when the universe gives us one brief chance to listen closely. Think of the galaxy as a slow conveyor belt. Every young solar system builds planets, and in the process, gravity flings leftover ice balls into the void. Most wander forever, but once in a long while, one crosses our path. If we read 3I Atlas cleanly, we don't just learn about a single traveler, we calibrate the belt itself. How many ejections does a typical star make? How cold are the shelves where their comets formed? How crusted do they become after ages between suns? Those answers turn a rare sighting into a census. Start with rates. Each interstellar visitor we catch tightens the estimate of how many exist per cubic light year. That number feeds back into models of planet birth. If the count is high, giant planets may be efficient slingshots that purge their neighborhoods. If the count is low, slingshots might be rarer or weaker. Harvard's urgency is really about locking down that rate with respectable error bars, because a shaky baseline today becomes a shaky theory tomorrow. Now think composition. Chemistry is a codebook. If 3I Atlas vents lots of carbon monoxide early, that hints at a birthplace colder or dimmer than our sun's nursery. If it stays dominated by water vapor until very near the sun, that suggests a warmer shelf. Dust texture adds another dimension. Fluffy grains point to gentle assembly. Compact grains point to more processing, collisions, heating, or long radiation damage. Put those clues together, and you can sketch a family portrait. Not just what this one object is, but what kind of solar system through it. Spin and shape whisper about construction. A slowly changing rotation implies gentle outgassing and a fairly symmetric body. A rotation that tumbles or accelerates tells you jets are uneven, vents are patchy, or the shape is lopsided. Even without crisp images, a well-measured light curve is like hearing footsteps behind a door. You can't see the person, but you can guess their stride and weight. But here's what makes this moment special. We're standing at the edge of a revolution in how we study these cosmic messengers. The next generation of telescopes is coming online, and they will change everything. The Vera Rubin Observatory will scan the entire visible sky every few nights, catching interstellar visitors weeks or months before they reach their peak brightness. The James Webb Space Telescope can dissect their spectra with unprecedented precision. Ground-based observatories are linking up in networks that never sleep. When that infrastructure matures, the era of scrambling to catch a single visitor will end. We'll have fleets of interstellar objects to study, compare, and categorize. We'll sort them by origin star type, by formation distance, by age. We'll build a periodic table of interstellar chemistry. We'll map the flow patterns of material between stars. What seems exotic today will become routine tomorrow. But that tomorrow depends on what we learn today. If we treat 3I Atlas carelessly, we lose more than one data point. We lose the chance to calibrate our methods, to learn which measurements matter most, to separate signal from noise. Before the flood begins, Harvard's urgency isn't about this single object. It's about building the foundation for a new kind of astronomy. So as 3I Atlas continues its ancient journey, carrying messages from a distant past toward an unknowable future, remember what you're witnessing. This isn't just a comet passing by. It's a preview of discoveries to come, a test run for humanity's expanding reach into the cosmos, and a reminder that even in our small corner of the galaxy, we're never truly alone. The universe is vast, dark, and full of wanderers. Some carry ice from alien suns. Some bear dust from foreign worlds. And every few years, one of them shares our sky long enough to tell its story. Our job is to listen, to learn, and to remember. Because in the end, these cosmic visitors don't just teach us about the galaxy out there, they teach us about our place within it. Why fold all of this into fear? Because stories harden fast. Tell the public too early that 3I Atlas is exotic, and you set up disappointment when ordinary physics explains the data. Tell them too early it's boring, and you train people to tune out when the next one arrives. Harvard's culture of caution is a guardrail against both mistakes. It says, stay faithful to the measurements, pace the narrative, and let updates move the needle. There's also a lesson about bias. Our instruments, schedules, and even our interests can create a streetlight effect where we mostly find what we're already looking for. Bright comets get more follow-up than faint ones. Night crews catch different phases than dawn crews. Spectrographs tuned for familiar gases may miss unusual ones. The antidote is intentional variety. Multiple telescopes, multiple wavelengths, north and south hemispheres, and pre-agreed checklists, so we don't steer unconsciously toward the expected. If you like mental models, think in terms of simple bets. Before data, your best bet is that 3I Atlas is a normal interstellar comet. Each clean measurement nudges that bet up or down. That's all Bayesian thinking means in everyday language. Start with a plain guess, then update it honestly as evidence arrives. The fear worth keeping is not of being wrong, but of refusing to update. There's a practical payoff to this discipline beyond astronomy. When a complex story unfolds in public, whether it's a medical trial, a new technology, or a mystery object in the sky, the same habits keep us sane. Write the questions down, measure independent ways, share the raw numbers, reward the people who change their minds when the data change. Harvard's push around 3I, Atlas is a case study in that culture. What about the romance of a chase mission? The idea of meeting a future visitor up close. Here, the rulebook we're writing becomes a flight plan. An interceptor needs 3 things: speed on short notice, instruments tuned to the gases and dust we care about, and a camera that can watch the spin and the jets in real time. A small craft could fly through the coma and scoop particles, while a companion stays farther out to track the big picture. None of it requires magic. It requires readiness, and readiness grows out of today's dry checklists. While we wait on engineering, the sky itself is generous. Even without a spacecraft, a coordinated watch can map the whole arc: quiet inbound, stressed swing by, cooling outbound. If we catch a burst, we learn about buried pockets of volatile ices. If we catch a lull, we learn about crusts that seal the surface. If we catch a steady push that matches a spinning vent's rhythm, we lock down ordinary jet physics across star systems. If we catch a mismatch that survives every ordinary explanation, then we zero in on the truly new. And that is the heart of the title question: why Harvard scientists fear what 3I, Atlas, really island. They do not fear the object. They fear a missed chance to separate noise from signal, to trade rumor for pattern, to turn a headline into a data point the next generation can trust. Fear, here, is just another word for respect for the cosmos, for the craft, and for the people who will read our notes long after this traveler is gone. So as you listen to the next update, try this checklist. Did the claim repeat on a second night? Did another team see it? Did more than one instrument type agree? Does a simple physical cause rise with the effect? If yes, relax into the result, whether it's ordinary or odd. If no, hold it lightly until the next baton in the relay comes through. Because the conveyor belt keeps moving, somewhere out there, another shard of someone else's beginning is already on its way. What we learn from 3I, Atlas decides how ready we'll be when the next knock comes on our door. What exactly do scientists fear when they talk about 3I, Atlas? Not monsters, mistakes. The nightmare is wasting a once-only chance because of sloppy calibration, impatient storytelling, or looking in the easy places instead of the right ones. If you understand those fears, you can follow every update with a clear head. Calibration first. Tiny errors make loud claims. A camera whose sensitivity drifts after maintenance can imitate a color change. A mount that tracks a touch too slowly can bias position measurements. Software that switches versions mid-campaign can alter how brightness is computed. None of this is glamorous, but this is where reliability is won. Good teams log the instrument state each night, re-observe standard stars to catch drift, and publish enough detail that rival groups can spot a problem before it becomes a headline. Story next. Once a narrative sticks completely normal or suspiciously odd, it pulls new data in its direction. The antidote is pre-commitment. Announce in advance what you will measure, how often you will measure it, and which thresholds will trigger extra observations. When the plan is public, it becomes hard to steer toward a preferred ending. That does not kill excitement, it protects it from us. Then the streetlight effect. We tend to search where it is bright, not where the truth hides. A northern observatory can miss a southern window. Spectrographs designed for familiar gases can glide past rare ones. Crews that work only at midnight can miss dawn surges. The cure is variety on purpose. North and south, optical and radio, big mirrors and small ones. long exposures and fast cadences. The goal is not one perfect dataset, it is many imperfect ones that agree. With those fears on the table, here is a no-jargon listener's guide to the signals you will hear about. Motion first. If an update says the orbit fit includes a non-gravitational term, that means a gentle push beyond gravity is present. Ask whether gas lines strengthened at the same time. If yes, picture jets breathing. If no, keep an ear out for follow-ups from different instruments. Chemistry next. Early carbon monoxide detections hint at a colder birthplace. Mostly water, close to the sun, suggests a warmer shelf. If the spectrum stays quiet while brightness climbs, think crusts or hidden vents. No single label is final. The pattern over weeks matters most. Then texture. Reports of high polarization usually translate to small, fresh dust grains. Lower polarization can mean smoother, larger grains or more processed material. Texture matters because it changes how sunlight scatters and how easily light pressure nudges debris, which affects how bright the coma looks and how we infer the size of the solid core. Finally, spin. When observers publish a light curve with a steady rhythm, rise and fall, they are taking the pulse of the nucleus. If small shifts in that rhythm follow a surge in activity, jets are doing work. If the rhythm is crisp, but chemistry is quiet, expect debate. Is the swing just shape, or is something hiding in plain sight? You will also see the same 3 public questions, again and again. Is it dangerous? No. A hyperbolic path means departure, not return. Will it be bright to the eye? Probably modest. Most of the drama is in instruments, not backyards. Could it be artificial? The sober answer is extraordinarily unlikely, followed by, that is why we measure. Ordinary explanations deserve the first, second, and third chances. Only when a mismatch survives, many independent checks do exotic ideas earn extra time. So what does a clean win for knowledge look like? 3 things. First, chemistry and motion move together. When gas lines grow, the gentle push grows, and the push direction follows the spin pattern. Second, the outbound fade behaves. Brightness, tail length, and activity fall along curves that simple heating and cooling can reproduce. Third, independent groups agree using different tools: optical spectra, radio lines, polarization, and precise positions rhyme. When those 3 land, the story is solid without hype. And what if the win is messy? That is not failure, it is a bigger frontier. Maybe the spectrum stays quiet while the push persists. Maybe dust texture evolves in an unexpected way. Maybe the light curve refuses to settle into one neat period, hinting at a tumble. Puzzles like these are invitations. Engineers learn what to build next. Theorists learn what to revise. Even "we don't know yet" is progress when it is backed by clean, shareable numbers. Legacy matters too. The method we practice on 3i, Atlas, becomes muscle memory for the next interstellar visitor. Checklists written in calm hours become reflexes on hectic nights. Shared logs prevent duplicated mistakes. Standard formats let skilled amateurs merge their light curves with professional archives without friction. Open notebooks make it easy for a rival team to find a bug in your code, and for you to thank them publicly. That is not weakness. That is how durable truth is built. Do not forget the human side. Curiosity can harden into certainty, and humility can be mistaken for indecision. Inside healthy teams, someone always asks, "What would prove us wrong?" And someone else says, "Spend 1 precious hour trying to break our favorite answer. That hour can save a month of noise." Here is a calm forecast you can keep without whiplash. Most likely, 3i. Atlas will act like a comet from another sun. It will wake, breathe, respond to sunlight with ordinary jets, and fade. In that outcome, the so-called Harvard fear will look like wisdom, because the careful habits sharpened now will shorten the path to certainty next time. Less likely, the object will keep 1 or 2 stubborn oddities alive across many checks. If that happens, the same habits, pre-commitment, variety, redundancy, will keep the debate honest and the conclusions stable. Either way, the story is worthy. A relic from a distant nursery is sharing our sky for a handful of weeks. We can meet it with discipline that future travelers will benefit from, or we can wing it and relearn old lessons. Choose discipline, and we trade fragile headlines for sturdy knowledge. Choose patience, and we leave a clearer map for the people who will watch the next stranger cross our sky. 3 ghosts haunt every discussion of 3I, Atlas. The first is Oumuamua, the interstellar sliver that showed no obvious tail yet drifted a whisper off gravity's chalk line. The second is Borisov, a textbook comet that looked ordinary while hinting at a colder origin through its chemistry. The third is our present visitor, clearly waking like a comet but still young enough to defy guesses. Those 3 set the tone for everything that follows. Expect surprises, but earn them. What did the first 2 teach us? Oumuamua proved curiosity can lose to the clock. By the time we realized how odd it was already fading. Borisov taught the opposite. Interstellar does not equal exotic. It vented, brightened, and behaved like a comet, reminding us that ordinary can still carry alien ingredients. Together they wrote the 3I Atlas playbook. Measure early, measure broadly, and let the chips fall where they may. Now demystify a few phrases you will hear as updates arrive. A non-gravitational term is a tiny extra push beyond the sun's pull. For most comets, that push comes from jets of gas. The trick is to see whether the push breathes with the spin stronger when a warm vent faces the sun, weaker when it rotates away, or whether it drifts too smoothly to pin on ordinary jets. Breathing argues for business as usual. A smooth drift that ignores the rhythm asks tougher questions. Dust-to-gas ratio sounds technical, but points to a picture you already know. Steam versus smoke. High gas with low dust is a clean kettle. High dust with modest gas is a smoky flare. Because dust looks dramatic, it can trick us about size. A small nucleus with a dusty coma can look larger than it is. A large, sealed nucleus can look modest. Knowing the ratio keeps our scale honest. Thermal models can sound like math class, but the idea is plain. Sunlight warms a surface that has day and night, like a turning world. Ices near the skin wake first, deeper pockets later, and strong sunshine can crack a crust like a pond in spring. If 3I Atlas wears a tough rind, little will happen until heat soaks in. If it is laced with fissures, activity may arrive in spurts. Either way, timing is a clue by itself. Spin is another. Most small bodies rotate around a stable axis, like a top. Some tumble, swapping axes as if the top were tripping on its shoelace. A stable spin writes a clean, repeating light curve. A tumble smears the rhythm or splits it into more than one beat. Jets can move a spin rate by tiny amounts over days or weeks. Watch those nudges and you can infer where vents sit and how forcefully they blow. Shape can be sketched from light alone. If brightness swings are large, nearly a factor of 2, the nucleus is probably elongated. If they are modest, it may be more rounded. Pair that with the spin rhythm, and you get a rough outline. Cigar, pancake, or potato. Add polarization and you add surface texture. Compact grains versus fluff. Press coverage often compresses all of this into a single word like anomaly. That is where audiences get whiplash. A color that looks too red one night can be twilight. A sharp brightening can be a geometry trick as the tail swings to reflect more sunlight toward Earth. An unexpected path tweak can vanish when another team adds 3 more nights of positions. Good practice treats each oddity as a question, not a conclusion. Repeat it, rotate it, and see if it survives new angles. You will also hear about phase angle, the triangle made by the sun, the object, and Earth. Change the angle and you change how dust sends light our way. That is why a comet can look calmer or wilder without changing. Smart teams compare nights with similar geometry before declaring that the object itself has changed. Against this backdrop, Harvard's worry takes a sharper form. We could write a bad first draft of the truth. Rush to weird, and trust erodes when the effect dissolves. rush to nothing to see, and we learn to ignore the very patterns that make science move. The antidote is patience in public. It is fair to say we don't know yet, and fairer still to explain what would move the needle and when we expect to know. The bigger stage matters too. Soon, next-generation surveys will push our sample from a handful of interstellar visitors to dozens. When that happens, the questions we sharpen now become statistical. Are interstellar comets colder on average? Do they crumble more easily? Do they favor certain spin rates or shapes? Are their dust grains typically fluffier from long radiation exposure between stars? One careful case today buys clarity across many cases tomorrow. What should you listen for in this phase of the 3I Atlas story? 3 pairings. Motion with chemistry. Does the gentle push grow as specific gas lines grow? Spin with brightness. Do rhythm changes align with vents turning into sunlight? And texture with color. Does a shift in polarization arrive with a shift in spectral slope that points to fresh, fine grains? When pairings move together, confidence climbs. If nothing pairs up, if every hint fades, we have still won something important. We will have measured an interstellar comet well enough to call it typical with a straight face. That baseline is a gift to the future. It means the next time a messenger from another sun writes its brief line across our sky, we will recognize the ordinary faster and isolate the truly new with less noise. In the end, fear is a misread of the mood. What you hear from careful scientists is not dread. It is stewardship. An ancient fragment from a distant nursery is passing through our daylight once. Our job is to listen cleanly, speak carefully, and leave notes sturdy enough that the next generation can build on them without reliving our mistakes. Here is a blueprint for next time the universe rings the doorbell. If 3I Atlas is our rehearsal, the first true sprint mission will greet an interstellar visitor in flight. No magic required, just readiness, smart staging, and instruments that ring truth from a fast, dusty encounter. Where should the spacecraft wait? Near Earth is convenient, but time kills opportunities. The moment a fresh interstellar object is flagged, the clock starts. Better to keep a probe in a high-energy parking lane around the sun, on hot standby with tanks mostly full. From there, a small push can bend its path toward the visitor. Think of a lifeguard standing at the pool's edge, not napping in the locker room. Propulsion is the first fork. Chemical engines deliver a quick leap, but burn fast. Electric propulsion ion, or Hall thrusters, sips propellant and builds big total speed with weeks of steady thrust. Solar sails give pure sunlight push with no fuel, but they demand big, delicate hardware and careful choreography near the Sunday. The practical answer is hybrid, a chemical kick for the sprint, then efficient electric thrust to fine-tune the chase. Navigation is the hard art. The target is faint, small, venting, and on a hyperbola, it will not hold still for our convenience. The guidance computer needs autonomy. It must see the target against a crowded starfield, ignore cosmic ray speckles and satellite streaks, and steer for itself in the last hours. Light speed delay makes joystick flying from Earth too slow. The craft must make its own micro-decisions. Shielding matters because dust does not care about our plans. Even a rice grain at tens of kilometers per second hits like a bullet. We angle approach vectors to skirt the densest parts of the coma and tail, add a Whipple shield, thin sacrificial layers that spread the impact and keep delicate sensors tucked behind the bus until the final minutes. In a perfect pass, the spacecraft crosses upstream of the nucleus first, then glides down the flow like a kayaker reading current. What rides along? 4 instruments cover almost everything ground teams crave. First, a camera pair, one wide for context, one narrow for detail, both with fast shutters to freeze motion. Their cadence reveals spin rhythm and jet geometry. Second, a UV-visible infrared spectrometer, the all-purpose sniffer that reads gas barcodes and dust colors across many wavelengths. Third, a polarimeter to measure how aligned scattered light is, and therefore how fluffy or compact the grains are. Fourth, a dust analyzer that catches tiny grains in aerogel or senses impact plasma and weighs their chemistry in real time. How close is close enough? For a nucleus a few hundred meters across, close can still be a few hundred kilometers. Any nearer, and risk rises fast, without a matching gain in knowledge. At that range, the nucleus spans dozens of pixels, jets trace arcs across the frame, and the dust analyzer sees a healthy drizzle without sandblasting the craft. The flyby lasts minutes, but the data rate is furious. Onboard compression and playlists chemistry first, then context ensure the most important bits get home. Communication is its own dance. A steerable high-gain antenna points at Earth between bursts of autonomous maneuvering. During the tightest turns, the craft stores data and focuses on survival. When geometry calms, it dumps packets in bursts. A small relay sat along the line of sight could help, but clever scheduling often does the job. There is a quiet hero here: pre-made software. Before discovery, teams run thousands of simulated chases. Bright target, faint target, quiet comet, violent comet, so the onboard brain has playbooks ready. When the real alert arrives, the craft is not improvising, it is choosing from rehearsed moves. What would such a mission buy that telescopes cannot? Parallax and proximity. From Earth, we infer spin from brightness wiggles. Up close, we watch surface patches rotate into sunlight and see jets at their roots. From Earth, we sniff blended gas. Up close, we smell the mix, vent by vent. From Earth, we argue about dust texture. Up close, the polarimeter and dust analyzer settle the debate with numbers. The result is a Rosetta Stone that lets us read remote data more confidently when we cannot fly. Even failures would teach. If autonomy struggles to hold lock in a blizzard of dust, we harden the vision system. If the Whipple shield takes a beating, we adjust approach geometry next time. If downlink schedules choke on data floods, we rewrite the priority stack. One daring pass could upgrade the field's habits for years. All of this sounds expensive, but the trick is modularity. Build a small, repeatable bus, keep instruments simple and flight-proven. Store one in that high-energy lane, and keep a twin on the ground, ready to launch when the next alert hits. We do not need to chase every visitor, only the ones bright and reachable enough to turn risk into knowledge. Bring this back to Harvard's fear. It is not fear of what the object is, it is fear of what we are not. Yet, ready, deliberate, agile. The more of that we bake into our plans, the less each new visitor feels like a panic, and the more it feels like a field exercise we trained for. And if 3I, Atlas itself, cannot be intercepted, that is fine. It can still be the rehearsal that writes the checklist, tunes the instruments, and justifies the hangar queen waiting in the sun's bright lanes. When the next knock comes tomorrow or years from now, we will not fumble for the keys. We will already be at the door, engines warm, questions sharp, and a plan built on the lesson this traveler taught us. Build yourself a simple scoreboard for 3I, Atlas, a quiet way to follow the story without whiplash from every headline. 4 dials are all you need: motion, chemistry, texture, and spin. When those dials move together in sensible ways, you can relax. When one wanders alone, you can get curious without getting carried away. Motion first. Imagine a clean chalk line on a blackboard, gravity's prediction. Observers plot the comet's position on that board night after night. If the dots hug the chalk line, motion is boring in the best sense. If they drift a little, that's the gentle push people talk about. Your scoreboard question is simple. Did the push rise and fall with the spin, like normal jets would do? If yes, that's green. If the push seems smooth and one-directional, ignoring the spin rhythm, mark yellow and wait for more nights and more teams to confirm. Chemistry is the ingredient list. A spectrum is just a rainbow split into bars where different molecules leave marks. Early carbon monoxide hints at a colder childhood. Water close to the sun hints at a warmer shelf. Your question isn't which molecule is cooler. It's, did chemistry change when activity changed? If the coma brightened and the gas lines grew, green. If the coma brightened but the lines stayed quiet, yellow. Maybe a crust is hiding the gas. Maybe the instruments missed faint lines. Or maybe dust did the heavy lifting. Texture is how the dust scatters light, red through polarization. Think of sunlight like jump ropes. Polarization tells you how lined up those ropes are after bouncing off grains. Fresh, tiny grains often mean higher polarization. Larger, smoother grains often mean lower. Your question: did texture shifts arrive alongside chemistry shifts? Green if those two sing together. Yellow if they don't, because geometry, twilight, and calibration can play tricks. Spin is the metronome. A light curve, brightness rising and falling, reveals the rhythm. Your question: do rhythm changes line up with moments when jets should kick harder? If yes, that supports ordinary causes. If the rhythm is crisp but nothing else changes, or if it smears unpredictably, mark yellow and let observers chase whether the body is tumbling, not spinning neatly. That's the private scoreboard. Now add a public filter that saves you time and nerves. When you see a claim, run 4 checks: repeatability, diversity, direction, and independence. Repeatability asks, did the same effect show up on more than one night? Diversity asks, did it show up in more than one kind of measurement positions? Spectra, polarization, radio. Direction asks, did the signal grow when its supposed cause grew, like gas lines rising alongside the push? Independence asks, did a rival team with a different telescope see it? 4 yeses mean confidence. Fewer yeses mean interesting, not settled. This is how you convert the so-called Harvard fear into a habit you can use in any complex story, not just a comet. Write your questions down. Look for patterns, not single fireworks. Keep an eye on your own hopes. Thrilling answers aren't more valuable than true ones. We don't know yet is not a failure. It's the honest stage between rumor and result. Let's also diffuse 3 phrases that often get twisted. Consistent with doesn't mean proven. It means fits the data we have without extra drama. Anomaly doesn't mean alien. It means we saw something we didn't predict. Now we try to break it. And no detection doesn't mean nothing happened. It can mean if it happened, it sat below our instrument's floor, or outside our wavelength, or behind moonlight. Scientists speak this way to protect clarity. You can use the same guardrails when you read. There's a deeper reason to keep your scoreboard calm. Stories fossilize quickly. If the first draft says weird, later corrections feel like letdowns, even when the corrections are better science. If the first draft says boring, later surprises look like hype, even when they're genuine. Harvard's whole posture checklists, cadence, cross-checks, is designed to keep the first draft elastic until the data harden. Notice how this discipline scales. Today, we have a handful of interstellar visitors. Soon, survey telescopes will push that number higher. When that happens, your scoreboard becomes a way to see patterns across the set. Do most interstellar comets wake earlier with carbon monoxide? Do they carry fluffier dust? Do their spins cluster in certain rhythms? One carefully told case today becomes a yardstick tomorrow. If 3I, Atlas ends up ordinary, that's a gift, a clean baseline. If it ends up quirky, that's a gift with homework. Tests will run on the next dozen to see if the quirk repeats. You can even use the scoreboard on the human side. Motion maps to momentum are teams sharing raw numbers fast enough to keep the analysis moving. Chemistry maps to culture are groups mixing methods and perspectives, or staying in narrow lanes. Texture maps to tone does the conversation welcome replication and doubt, or punish it. Spin maps to pacing, are we letting the story breathe, or chasing daily swings that mean little? When these 4 line up, communities learn faster, and when arguments flare, as they will remember the quiet superpower of pre-registration. When teams say in advance, if X rises above Y for Z nights, we will spend N hours doing Q, they remove the temptation to move goalposts after the fact. The public sees the plan, sees the trigger, and sees the follow-through. Trust grows. That is not drama. That is rigor in plain view. Pull back one more time to the title question. Why do Harvard scientists fear what 3I Atlas really is? Because really is earned, not presumed. They fear a premature adjective, exotic or boring, hardening into truth before the measurements have had their say. The antidote is small and sturdy, a shared scoreboard, a patient cadence, a taste for replication, and a willingness to be surprised by ordinary physics. If you step outside tonight, the scoreboard fades and something older takes over. Above you, a dark traveler from a different sunrise is tracing a one-time curve through our sky. It has no opinion about our headlines. It will not slow if we argue. It will not brighten to reward our attention. It will simply pass as billions have passed unseen. Our job is simple enough to be noble. Point the instruments, keep good notes, and let the truth arrive at its natural speed. Carry that habit into whatever you learn next, and you will do what the best scientists do. You will trade noise for pattern. You will keep your wonder without selling your judgment. And when the next knock comes on the cosmic door, you will already have a place at the table and a clear, calm way to listen. Call this the quiet ending, the one where the visitor keeps its secrets politely and still leaves us wiser. 3I Atlas is not a prophecy, it is a mirror. When we stare at a traveler from another sun, we see our habits reflected back, our patience, our blind spots, our appetite for wonder. Harvard's caution is not the star of the story, it is the lighting rig that lets us see the stage clearly. With that light on, the scene sharpens. An ancient object warms, breathes, arcs past the sun, and then slides into the dark again. No fireworks needed, just clarity. Begin with what will almost certainly be true when the curtain falls. We will know the path in fine detail, how fast the comet arrived, how hard the sun's pull bent it, how quickly it will fade into interstellar night. We will know the spin rhythm well enough to say whether jets nudged it or merely tickled it. We will know the broad strokes of chemistry, whether early carbon monoxide whispered of a colder nursery, or whether water dominated until late, pointing to a warmer shelf. We will know the texture of its dust from how light lined up after bouncing off those grains. And we will know, with adult confidence, that interstellar means passing through, not danger. The hyperbola is a goodbye written in geometry. Now admit what we will likely still not know. We may not pin the nucleus's shape beyond a family resemblance, elongated, rounded, or something between. We may not map every vent or crack that opened during the swing-by. We may not lock the dust-to-gas ratio to the last digit. Comets are messy, and instruments have limits. That is fine. Science is comfortable with enough to move on. The next wanderer will land where this one leaves off, and our questions will already be sharper. Here is the thread to carry forward. We learned to keep a simple scoreboard motion, chemistry, texture, spin, and to watch for pairings that move together. That habit will outlive this object. It will shape press briefings, telescope schedules, and the way classrooms talk about interstellar things. It also travels well beyond astronomy. Any complex public story, medicine, climate, technology, benefits from the same quiet discipline. Define the dials, name the thresholds, and let patterns, not vibes, carry the weight. There is a civic lesson too. When researchers show their logs, pre-register thresholds, and invite rivals to replicate, they are not performing for applause, they are building trust. If you felt calmer during this story than you did in 2017, that is why the culture matured, the language got clearer. Consistent with, and no detection stopped sounding like evasions, and started sounding like what they are honest status reports on the way to an answer. But the ending we most deserve is older and simpler. Step outside at night and imagine the arc you cannot see. Somewhere above your roofline 3I, Atlas is tracing a curve no one can bend into a circle. You are standing on a small world that loops the sun every year, lit by a star, ordinary as stars go. in a galaxy that has thrown countless objects into the dark. And yet, right now, one of those objects is here. It is not here for us, but it is here. That alone is enough to feel lucky. Be clear about the fear in our title one last time. Fear of missing a measurement is not fear of the unknown. The unknown is our workplace. What we want to avoid is wasting the chance to turn fleeting light into lasting sense. That is why checklists mattered, why cadence mattered, why independent teams mattered, why skilled amateurs mattered, why simple, repeated questions beat complicated one-night stunts. The discipline was the point. The visitor was the gift. What happens after the fade? The numbers take second lives. Modelers fold them into simulations of planet birth and ejection. Observers use the light curves and spectra as training data for the next midnight alert. Engineers treat the dust readings and geometry lessons as footnotes for a future chase mission. Students read a paper and hear, in its dry tables, the echo of a few frantic weeks when a distant sunrise sent us a snowball and we answered with craft instead of noise. That is how a brief flyby becomes a durable page in our book. And you get something too. You get a template for listening without losing your balance. The next time a headline blares, you can ask 4 calm questions. Did it repeat? Did different tools see it? Did cause and effect rise together? Did arrival confirm? You might not trend with that posture, but you will be right more often, and you will enjoy genuine surprises more because you did not spend your attention on mirages. So we end where we began, with a visitor that shouldn't exist. If you think of the solar system as a closed room, it isn't closed. The door is open. Once in a while, a traveler wanders through and reminds us our neighborhood has neighbors. Some will look ordinary and teach us patience. Some will look odd and teach us humility. All of them will reward preparation. The smartest fear is simply that we might not be ready when wonder shows up. If you remember one sentence from this whole story, let it be this: curiosity is a craft. It is not a mood that comes and goes with headlines. It is work, quiet, repeated, sometimes dull, always hopeful, that turns one-time visitors into lasting understanding. 3i. Atlas will go. The craft can stay. Keep your scoreboard. Keep your questions. Keep your welcome mat out for the next knock on the cosmic door. And when that knock comes, we will meet it the way we met this one, with clear eyes, steady hands, and the kind of courage that looks boring from a distance. The courage to measure first, wonder second, and speak only when the evidence can stand on its own. In a few weeks, 3i, Atlas, will look like it always did to the universe, just another cold traveler sliding back into night. But it will not look the same to us. We will have asked better questions, compared cleaner numbers, and learned how to keep our balance when wonder walks by. That is the quiet power at the heart of this story. Readiness over hype, patience over panic, craft over noise. If you carry only a handful of ideas from this journey, make them light enough to keep. First, interstellar does not mean dangerous. A hyperbola is a farewell written in geometry. Second, ordinary is not an insult. A visitor that behaves like a comet still teaches us about other suns, how cold their nurseries were, how their dust is built, how time hardens a surface between stars. Third, mystery is not a license, it is an invitation. We honor it by measuring first, imagining second, and letting the evidence decide when a surprise is real. You do not need equations to follow the plot. Motion tells us whether a gentle push rides along with gravity. Chemistry tells us which ices wake and when. Texture tells us how dust scatters light. Spin tells us the rhythm of vents turning into the Sunday. When those 4 dials move together, the story writes itself. When one wanders alone, we pause, repeat, and ask a sharper question before we reach for headlines. Harvard's fear was never fear of aliens or disaster. It was the fear of throwing away a clean experiment. The cure looked boring from the outside: checklists, cadence, shared logs, rival teams double-checking each other. But boring is how fragile truth survives. In a world that runs on speed, The bravest move was to slow down just enough to be sure. When we did, nuance returned. Words like consistent with and no detection stopped sounding coy and started sounding careful. Even our dead ends pay rent. If the spectra stay quiet while the coma brightens, we learn about crusts that bottle gas. If the push follows the spin, we calibrate jet physics under a different star. If a suspected flash turns out to be a satellite, we test how to kill rumors kindly and quickly. Every tidy correction is a tool the next team will reach for in the dark, and there will be a next time. Survey telescopes are about to widen the door, turning rare into routine. When the conveyor belt brings the next wanderer, we will not be starting from scratch. We will have a scoreboard ready, a cadence chart on the wall, and a respectful culture that lets patient answers outrun dazzling guesses. If engineering allows, a small interceptor may even be loitering in the sun's bright lanes, rehearsed and waiting to sprint. What does this leave you with tonight? Under your own sky? Maybe just this: between stars, there is no traffic cop, no path laid down, only long arcs written by gravity and time. Once in a while, one of those arcs passes through our daylight. We cannot keep it, we can keep the meaning. We do that by pointing our instruments, comparing our notes, and telling the truth as cleanly as we can manage. So let the visitor go. Let it carry our attention back into the dark. What stays behind is better than certainty. It is competence. We are a little more practiced at listening, a little less vulnerable to noise, and a lot more ready for the next knock on the cosmic door. That is the prize we get to keep. And when the future brings a stranger with a deeper riddle, we will meet it the way we learned here, with clear eyes, steady hands, and curiosity treated as a craft. We will measure, we will wonder, and then we will speak only as loudly as the evidence can bear. If that sounds quiet for an ending, good. Quiet is where signal lives.